Hello everybody. We're going to work on multiple regression today. So I loaded in the Glen Cove data file. And we did this by read.csv file.choose. Your file has to be in CSV format for this to work. I made a mistake. That's what the plus represents. I like to every now and then make these silly mistakes so you get familiar with mistakes and don't get baffled, don't get embarrassed, just work around them. That plus mistakes meant I missed a parentheses, and so I closed my parentheses and I was able to then load in my Glen Cove data set. I attach, you don't have to do this, I don't think anymore. This is just me being a dinosaur, and so I attached the headers, and then I did the head Cove one because I like to see what my data set looks like. And so what we have is we have the street address of these houses in Glen Cove, New York. We have the fair market value, we have the property size in acres, we have the age of the house, and we have these other variables. We're going to use these other variables later when I talk about finding the best fit model. So model fitting. Look for that video later. Today, I want to try to predict market value utilizing acreage and house age. So house age, acreage, can it predict, and how well does it predict fair market value? To do that, I need to load it in as a linear model, and that's what this does right here. Fit1, we'll call it. We load it in as a linear model, and I utilize the fact that I want to predict fair market value, tilde, property size plus age. If you're having troubles read this, that's because your original CSV file has either numbers, dollar signs, anything that could be causing commotions when you load it in. You might want to call this FMV, just short it as fair market value. And this could just be acreage, and this could just be age. All right, the reason that the ... there might be some extraneous variables up there that R is having trouble loading in. All right, it works for me for this case. I can load it in. And then I use the summary of my model. So again, we're doing a linear regression, a multiple linear regression. That's why the LM. There are many other things you could do with LM. There's extra components here. I just needed the y tilde x1 plus x2, and then I did a summary call. Upon the summary call, there's so much information to get just from this summary page. And I want to bring up my little file here on the side because it's best just to explain it one by one. First of all, you got the prediction equation, all right? That's the first thing to be able to see is in RStudio, can you read the variables here? Can you read the intercept? That is known as the y-intercept variable. Can you read the acreage slope? Can you read the age slope? These are partial slopes. So what do they mean? What do they represent? That's the next thing. The next thing you got to be able to do after you get the prediction equation is be able to explain each piece of that equation. That's very important. So for example, the y-intercept, what is that? Well, that's the estimated mean house value in thousands when there is no acreage and it is 0 days old. Of course, how can you have no acreage? Well, if your house is back to back on top of everybody else's houses. Can it be 0 days old? I guess it could be brand new, but brand new, we're looking at $500,000 in this area, estimated. At any time, I would pause the video and take a look at what I've written and the notes so you can also take your own notes. All right, slope of x1. What's the slope of x1? Well, my x1 variable here, the 407, represents acreage. So we're talking about the slope of the acreage. What does that mean? Well, this is now partial slopes. So you got to be careful. So for a given fixed age, we fix the age of the house. Once we fix the age of the house, the other variable, then each increase in acreage, one acreage, remember, it's always changing y over changing x. So when we increase the acreage, the estimated result in the mean house value increases to about $407,000. All right. So again, fix the age, each increase of 1 acre, we get an estimated result increase in house value of $407,000. Think about that. Think about the fact if you let x1 be 1 and x2 be 0, right? When you plug in, x1 is 1 for 1 acre, x2 is 0, being their house is brand new, 407 plus 532, we're at almost $1 million house when you have the house plus 1 acre of land. That's very important to understand when you're evaluating your your multivariable equation, you know what x1 and x2 represent. X1 is acreage, x2 is age of the house. So if we're looking at a 1 acre house, 0 days old, so brand new, it'd be 1, so 407 plus 532. So about 900, what is that, $39,000 for a brand new house with 1 acreage of land in Glen Cove. All right, let's look at slope of x2, the slope of the age. What this says, now we got to fix acreage. So fix the acreage. Then, if we increase the age of the house, the estimated result in the mean decrease, and these are always about the average decrease when we're looking at the slopes here now, the mean decrease in the market value is about $2.8 thousand. So we lose about $2.8 thousand every time a year goes up, the age of the house goes up. So after 1 year, we've lost 2.8 thousand. After 2 years, we lose about $5,000. So we got to understand what X2 does. It is the loss in the market value of the house based on the age. Excellent. All right, so what else do we get from our summary? So much. We get the F statistic right here. What is the F statistic? Again, guys, read your chapter, read your statistics book. All right, Google what is the F statistic in multiple regression, what it means. What I'm doing here is going through an example to help you summarize. So overall, the F test for significance, it has an F stat of 31.32, as you can see, with a p-value, might as well call it 0. This means at least one of the slopes is non-zero. And so what we have is a linear relationship between the dependent variable and at least one of the independent variables. So overall, we've got a good model. We're not sure if both of the variables are needed, but the F statistic shows overall there's significance in the model. So what do we do now? Well, then we go to the t-test right here on each slope separately, the t-test and the p-values for each of the slopes. So the t-test for age, t-value is negative 415 with a p-value, well, as you can see, 0.0003. And this means we have evidence that age contributes to the model, and the t-stat on the size is even smaller p-value, and that means we have evidence that property size contributes to the model. So notice the 3 hypothesis tests we have here. We have the overall F test, which is significance of the model in general. And then we have specific t-test, which is looking at each of the variables and how they contribute to the model, if they're significant to the model or not. That's very important to understand what each test means, what each null hypothesis is, so you can understand what it means to reject and not reject. That's very important. So you should write those down. All right, after this, we could continue on with our commands. So let me go, and we can build a confidence interval, as you see here. You can run the confidence interval on the model, which in this case is fit 1, and you just tell the level of the confidence interval. You're looking for a 95% confidence interval, run a 0.95. I did that, as you can see, and I wrote it over here. Again, what I would do is pause and then write down the code. Honestly, after every time I get the code to run right, I copy and paste that code into a Word file or a Notepad file so I can look at it later, and then I write down exactly what it means, just like I did here. For example, if I want the 95% confidence for the true slope of age, all right? Remember, we have a sample slope here. We have a sample of houses. We didn't get every single house. We have a sample of houses. So our slopes, our sample slopes, are B1 and B2. If I want the true slope, our beta 1 and our beta 2, well, I can build the confidence value for the true slope of age, and that is between negative 4.2 and negative 1.4. What does it mean to me? Well, to me, it's important that 0 is not in this interval. It's just another test of significance. If 0 is in the interval, then the slope could have been 0, and it probably would have set up here the t-stat would have not been so critical. 0 is not in this interval, which tells me age truly is a significant slope. Vice versa, that's exactly what this says. So they're kind of checking each other. The p-value here is significant. The fact that 0 is not in this interval is significant. Same thing for acreage, all right? Other things we can utilize here is, let's say we're going into a poor market year. We're going into a poor market year, you can say, could I reduce the slope? For example, the acreage slope is 407. Could I reduce this and get a reduction in market value? The answer is yes. you could utilize this lower edge, 274, and when you replace the 407 by 274 in the prediction equation, you would definitely get a lower market value by $200,000 per prediction. And that's quite a substantial prediction reduction. All of this happens when you're trying to make predictions. What type of market value are predicting for the future? I'd use the typical slope of 407. If you think you're going into a bad market, maybe you go down to 274. You think you're going into a good market, maybe use the upper bound on the confidence interval on acreage and use 540. There are many, many reasons we would utilize these lower bounds and upper bounds on slopes depending on the market we're going into. It's nice to have a confidence interval on this true slope, though, for age or acreage. Excellent. What else do we get from this summary? Well, from the summary, you also get the multiple R squared and the adjusted R squared. When we're doing multiple regression, I like the adjusted R squared. The reason being is if you pick a lot of variables in your multiple regression model, all those variables could confound each other. It causes the variation to inflate, which we'll all talk about later in later videos. But right now, since we only have two variables, I can keep it straight and say the adjusted R squared is really, really excellent at 67.65% of the variation in the market value is explained by the model with adjustments for the number of variables and sample size. Again, we have two variables. All right, if I had more, like we could have more, we could have, what is that up there? 1, 2, 3, 4, 5, 6 variables, it looks like I have for later choice. Those could add and inflate the R squared value, the multiple R squared value. The adjusted R squared adjusts for the number of variables, and that's good. What I'm always looking for, though, is a small gap between R squared and adjusted R squared. What's a small gap? You have to use your logic. But a small gap between R squared and adjusted R squared usually means we've got the best variables and we have what everybody looks for, parsimony. So what we have here, over here, for multiple R squared and adjusted R squared, they're really close, 69%, 67%. You're off by about 2%. I would say that's a really close. And in fact, I love the adjusted R squared. Again, I want to know, do I have the variables that really mean the most? Well, think about this. 60% of the reason the market value goes up and down on your house, 60% of the reason your market value will vary is based, according to my model, on two things, the age and the acreage. Now, this should be obvious. Age of the house matters, acreage matters. And so, again, we're not doing anything big, but it does help me really seal the deal on what this does. 67% of the reason market value fluctuates at this neighborhood is based on those two variables. After we have done some cool analysis, it's always important to do the residual analysis. If our rule one, if our residuals are not accurate, then and our residuals do not pass, all right, their tests, all the things I've said for the last 15 minutes mean nothing. So what we need to do is we need to run the residual analysis. To run the residual analysis, first and foremost, just plot the model. So we plot it one. And then it's going to bring up four things for you to plot. So we hit return. Boom, our first plot. Our first plot is for the linearity. Remember, we're going to check LINE, right? Linearity, independence, normality, and equal variance. So what we have here is I'm looking at linearity and equal variance in terms of the overall model. When I look left to right, I want a roughly even spread, not too many issues. It looks like 0.10, data point 10 might be an issue. Everything else looks pretty evenly spread, and so I'm looking pretty good in my linearity. I'm looking for a nice scatter. I'm looking for, no growth, no decay. So I'm looking pretty good for the overall model. All right, second plot of this plot, for fit one, is the normal QQ plot. This is the normality of the line check. So we've done the L and E check, linearity and equal variance. Now we need to do the normality check. The normality check is, again, if you've done simple linear regression, multiple regression is very similar. So we look along here, we look to make sure most of my data points are pretty tight to this line. Looks like 0.10, maybe 0.28 are a little off. There's not major bends or major deviations. So again, besides 0.10, data point 10, we're looking pretty good. I now am starting to think I might have to investigate point 10 in future investigations. All right, let's continue. We have the scale location, not so worried about that. And then you also have Cook's distance, which is a measure for influential points and outliers. Now, this is a great example where I love Cook's distance. The dotted lines are, if you are past these dotted lines, you're influential or outliers. And so these really are my bounds. And right there, point 10 is right on that boundary line for a Cook's distance. And that really is a point we should investigate. And so what does that mean? Well, if you pause and think about it, if you have an influential point or an outlier, you should remove it and redo the analysis. I'll let you do that. I'll let you think about that for future and try it out on your own. Again, if we have an influential point, what I would do is I would do the analysis all the way through with the point and the analysis without the point, compare and contrast. This is very important that we have a battle plan when we have an influential point or an outlier. Now, we are multiple regression. Multiple regression means we should also look at the residuals per each slope. What does that mean? We should plot each individual variable. For example, we have the property size. There it is, property size in acres. And we should measure that according to the model's residuals. We should plot those residuals against the x variable and see if there's any type of pattern. Well, when I look at this data set, when I look at this plot, which is the x1 versus the residuals, I am a little concerned because it looks like we're really clumping in here and then dying out. That means I might not have equal variance here. Maybe when I get rid of this outlier, if that's still the outlier, then this all becomes nice equal scatter and I'm not worried anymore. So again, this is definitely a good example where getting rid of an outlier might be beneficial. All right, after that plot, we would now plot the age of the property. So we plot the age of the property, age x2, against the fitted residuals. You should do this for each variable. You do not want to see a pattern for any one of these variables. There's no pattern here, equal scatter. Why are we doing this? Because even though the overall general model looked safe, I want to make sure none of the variables inside of the model needs a transform. If it does, and we'll look at this later in future videos, then we will transform it. If I saw a pattern, for example, in the age, like I think I see a bend, then maybe a square root of age might work better in my model to make my residuals scattered. We always want to make sure linearity and equal variance is true in each of the individual variables. Again, this could just be a squeezed in picture, and so really the model is really scattered, or there could be a bend there. And we might want to look into, again, a transform just on the age variable to settle down this bend if there is one. I'm curious about getting rid of that outlier and seeing if that settles everything down once again. If you notice, I keep repeating that outlier because I'm wondering about that. Cool. So we've checked linearity for the full model. Sorry, linearity and equal variance for the full model. We checked linearity and equal variance for each individual x value, and you should do that. And we also checked the normality of the model. The only thing left is to check for independence. And how we check for independence is we check it by running the Turbine-Watson. Now, as my notes say, right here, so we are going to work on the independence. And to work on the independence, first of all, that would be the Turbine-Watson test. The Turbine-Watson test, you have to load a separate library, all right? So your library you got to load is the LM test library. After loading the LM test library, you can run the Turbine-Watson test on your model. Boom, there's your Turbine-Watson test. Your Turbine-Watson test is a test for autocorrelation. Autocorrelation means there is no independence in the residuals. So what we have here is we have our Turbine-Watson statistic, we have its p-value. And in this case, a big p-value is actually what you want. I know that sounds funny. You got to understand your test. Notice, true autocorrelation is greater than 0 means we have autocorrelation. We don't want that. So we actually don't want to reject here. And since our p-value is big, and if you notice, I haven't been paying much attention to an alpha of 5 or 10 or 1%, is because most of my significant values have been close to 0. I should have been careful of that. I would have noted if any of my p-values were in the 1%, the 5%, or 10% range, as I call it, the gray range, I would have been more careful. But most of my values for my p-values up here have been close to 0. And that means they are significantly awesome. That is, no matter what you choose for alpha, 10, 5, or 1%, you're going to reject all of those. And rejection up here is important because that means you have significant slopes and significant combinations. Down here, it's important that we have a p-value that's greater than alpha. And then notice 94% is greater than pretty much any alpha you can ask for, 1, 5, or 10. Usually we stick with the 1, 5, or 10% numbers. So in this case, we want to not reject, which means we have independence, and that is a good thing. So we have independence checked off. Really, the only thing that I'm looking into is that outlier, and we should look into that, and I did. And to check for outliers, you run the Cook's distance. So call Cook1, I load it into Cook1, and Cook's distance should pop up nicely on your model. And then you can plot the Cook's distance. And there you have it. There is clearly one point that is so far away that we should investigate. That 10th point, we should investigate that point. That point could settle down my equivariance and linearity on that 1x variable, or maybe not. There might be a transform needed. But right now, I think I need to take that point out and redo my analysis. Of course, I'll leave that for you. Thank you so much for paying attention to our first video on multiple regression. I hope to see you soon for more.